It's a big
I'm
pleasure.
happy to see you, of course. Yeah.
Oops. Very happy to see you again. How's life? Well,
Yeah,
we'll
me
catch
too.
up. We'll catch up later. Sorry.
Yeah.
All right. So let me switch things around a little bit. So I'm going to share my screen, and I'm going to share my screen. You should see my slide and a tiny me here in the corner. Correct? All right. Beautiful. Okay. So. And then I will need this thing here. All right, so let's talk a little bit of the history of human-machine interaction. And let's start with tools. And because like if you think about it in a very abstract way, the very early use of, or the very earliest considerations in human-machine interaction was the way we used and tools and the way we design tools. And actually, tool using is by many considered to be the trait that defines us as humans, the trait that it defines us as unique in the animal kingdom. That's not entirely true. There's many other animals that are out there that use tools, but for us, it's definitely one of the most, together with language, is one of the things that really defines us. And very interestingly, for example, if you think about the history of how do we consider our own history, it has been typically defined in the form of ages, the Bronze Age, the Iron Age, whatever, which it actually does refer to the materials that we use to create tools with, which I think it's actually quite interesting. Now, the tools that we used in the past during our civilization history were not always considered for utilitarian purposes. Actually, in the history of humankind, we have used a lot of tools for the sake of art, for the sake of personal expression, for the sake of reaching other non-tangible, non-functional goals, if you will. And the purpose of this in history has been kind of unclear. We don't know why people were painting animals in caves, etc. But what we do know is that the art of using tools has, for the sake of many, many centuries, been associated to craftsmanship, and craftspeople, the people who were experts in the use of tools, have had a very important role in the history of our evolution in civilization. A sign of that, for example, is the fact that people who knew how to use tools and make physical artifacts associated themselves in things that we call guilds. And there was a certain level of what we would call in modern times intellectual property, secrecy, the idea of techniques and the know-how of how to use materials and tools being passed around generations and kept secret in these clubs that capitalized on these techniques because they had value. They were relevant to humanity and they were relevant to people who use these tools, right? So much that many modern authors have highlighted the importance of the relation between humans and tools. Like, for example, Richard Sennett writes, so unitary and so concentrated was the process, that the notion of design, that the notion of thinking artifacts, considering the design of an artifact, didn't exist, never. It was never detached from that of making things. There was no, back in the times, there was no, I'm going to design something and then I'm going to make something as two separate processes. They were both embodied in the hands and the mind on the craftspeople and what elevated to the art of craft, correct? So this was a very interesting period where making things was intimately associated to the humans that were making them and to the tools that we used to make those things. Now, at some point, end of the 18th century, end of the 19th century, whatever you want to place that relation changed dramatically. And it changed because with the advent of the Industrial Revolution, we became really, really good at mass manufacturing identical objects via mechanical processes, which had a lot of advantages. It made things very cheap for everyone to acquire. It started the era of consumerism. It made availability and accessibility to material resources much more widespread. But it also had a lot of social and economic implications, as we already know. Think about this. Before the Industrial Revolution, every single object that every single human owned had been made by another human with their hands. And there had been a process of thinking about that process. There was mindfulness in every single object that existed in the world. Industrial Revolution changed that. And one of the most drastic changes was that using tools stopped being an art, stopped being a craft, because craft turned into labor. The tools that we used to make things were not directed towards designing those things, but it was directed towards operating that things. It was about the control of the energy that went into those machines, not anymore about the form or the decisions that were involved in making those objects. And therefore, there was no relation. There was such a loss of relation with that tool that many authors at the beginning of the 20th century started talking about the alienation that humans felt with the use of machines and this new relation with making things. It became so bad at some point that many authors started advocating and created this movement in the early 20th century called the arts and crafts, which was intended to be a comeback, was intended to advocate for people going back to the old good times of this human tool material unison, right? And but in the context of the Industrial Revolution, the arts and crafts was also very importantly seen as a liberating movement against the alienation of machines making mass manufactured artifacts. The arts and crafts was advertised and was embraced by many as a movement that freed people from the slavery of the machines that produce things and brought them back to the holy times of making things by hand and the value of craftsmanship and things made with the hands. Now, this in principle was an interesting motion, but there were already many other people who were also arguing that this idea, the liberating idea behind the arts and crafts, was a little bit of BS. Was not really a thing. Just because thinking of a hobby as a liberating movement against the slavery of the social and the economic slavery of the Industrial Revolution was naive at the end of the day. And if you actually read the documents by Mary Ward Bennett, who, by the way, was one of the most interesting characters at the beginning of the 20th century. She was a women's rights activist. She was a pacifist. She was a pioneer. She advocated for birth control, women's suffrage, sex education. She was a really, really interesting person at the beginning of the 20th century. And she was one of the ones behind advocating that the arts and crafts was no liberation movement whatsoever. And that if we wanted to liberate ourselves from the slavery of the machine, then deep economic and social changes had to be in place for that. Nevertheless, this idea that having a job during the day, but then doing your thing as a side, as a way of channeling your creativity, kind of stayed since that moment. And it has still permeated today to our days a little bit by many authors who, for example, consider art as an experience and who have written philosophical essays about how an object can have an expressive value, which is part of the process of how it's made. And it's no longer an object, but it's more of a work of art that embodies an experience. And therefore, what is important for these authors is the idea that the experience is bringing back together the thinking of an object, the designing of an object, and the way you make that object at the same time, which again was the big separation, the big divide that the Industrial Revolution brought to making physical objects. Many other authors. Oops.
No worries.
Should I continue?
Yes, go please.
Jose, your face is just a little laggy. I don't know if maybe you're recording on your end.
I'm not. I'm not recording on my end.
Okay.
It might be my connection. I don't know.
Okay. Sorry.
Yeah, don't worries. So yeah, so this idea has still made it to our days with the modern, for example, the modern FAF movements, and the idea that that owning and bringing back machines that can make physical artifacts and make them available to everyone has also a liberating effect through technological empowerment, through economic empowerment, and through the intellectual liberation that being able to produce physical things can bring outside of real industry. And that's a little bit of where the Fab Academy and the do-it-yourself movement is situating itself these days. Now, but if we go back to making things, so with the Industrial Revolution came mass production, et cetera, but with the second Industrial Revolution came more technology, came more white-collar jobs, and a lot of advances in computation made making physical things different. For example, the invention of CNC machines and the invention of customizing the way we make physical artifacts using code was actually quite a novel idea, especially in the 50s, where these ideas started coming to fruition. There's this really interesting article about using punch tapes and machines that can be numerically controlled, and how the liberation of Joe Workshopper, this guy here, the liberation of Joe Workshopper was going to come through these machines that would allow him to, you're frozen? Are you still there? Yeah, okay, yeah. And how the liberation would come in his workshop with these intelligent machines that would make all sorts of artifacts for him. It's a super interesting article. I would really recommend that you read it, because it comes with a lot of predictions that came true. For example, the downscaling of those machines that you see here in the lab to small machines that will be owned by everyone. And that is kind of happening these days with 3D printers. The creation of blueprints, so the punch tapes and the code that runs these machines as a job. And that is also happening these days. So the idea of computer scientists or people who can make their own G code, et cetera, is also happening. But also many other predictions that were like super far-fetched and never actually happened. So for example, the control of these machines not being affordable, or the expenses of creating those blueprints being always out of the scope of the average Joe Workshopper. Today, the discussion is what is happening with the third industrial revolution. The idea that we're moving somehow from industry and heavy machinery to a more high-tech environment where the distinction between making mass production and customized is not so strong anymore, just because all the machines that we use to make physical things are digital, and the promise that all the objects that we will make will be mass customized and will have a level of personalization, etc. That's kind of where we are today. But very interestingly, the idea that machines and computers and technology will eventually and gradually start displacing the role that humans have in making physical things was already drafted and was already preached in the 60s by this gentleman, Norbert Wiener, who was already saying way before we had the conversations way before we had these conversations about AI and robots taking our jobs, etc. He was already saying that the technological advances that we were witnessing were displacing human labor in a way that was making us not competitive with machines anymore. And as soon as new machines came in that were able to compete with our brain labor, so for example, artificial intelligence, neural networks, being able to compete with the way we think, then at that point, when when the second industrial revolution is accomplished, the average human being that could not compete in skill and in strength with physical machines and could not compete in brain power with artificial intelligence will have nothing else to sell and will remain mediocre and will have nothing that is worth for anyone to buy. This being heard in the 60s may sound kind of apocalyptic, but this is 50 years later is the ground of the conversation that we're having these days about robots and neural networks taking over our jobs, which I think is something to consider. I think the good news is that for all of those who are here and are interested in pursuing and bringing your brain to a higher state, I think you are in a good position, but definitely we need to consider that we need to keep competing with all this artificial intelligence that we are creating to compete against ourselves. Any questions, comments before I continue? Let's take a look. Let's take a look then at this idea, this idea of separation between doing things and thinking things, but in the context of architecture. Let's take a look at that because that separation has even a longer history, if you will, because just as with making physical artifacts, the idea of thinking a building and making that building had never been detached, had been also a one single unitary process since the dawn of humanity. You will be surprised about how little planning and how little forward thinking there was in making physical buildings, even large scale, expensive, fancy ones, so religious architecture for many centuries. That was not really, it was like very much designed in place and there was little planning. And one of the best documents that we have is this plan of the cloister of St. Gall in Switzerland, which is believed to be theoretical. It's not believed to be an actual construction drawing for the monastery. So it was a very ad hoc, it was a very in-place process that was led by the master builder or the master mason or this one mind that had design and making buildings together in their mind. It wasn't until the Renaissance with Alberti and his book, De Re Edificatoria, who coined for the first time the concept that buildings could be represented by a set of notational systems that he called the lineamenta, and that became the origins of what we call nowadays blueprints. The idea that a building could be represented by something so abstract and so imperceptible by us humans as, for example, a section cut through a horizontal plane, that had never been a thing until the Renaissance. But the idea that this was a possible way of representing a building so that someone could design a building through a set of notational elements and give those notational elements to a second person who would be able to reconstruct or to build that artifact out of that notational system. That was so groundbreaking. That was a huge paradigm shift that happened in the Renaissance, and that became the new form of designing architecture that has permeated until our days today. And today, no one thinks about showing up on site and improvising a building anymore. Buildings have to be absolutely designed up to the minimum detail in documents, and then they're handed off to someone else who may or may not make that without any communication with the original architect. That is the staple today. That was invented in the Renaissance as a concept. And in a way, it also meant this breakthrough of separating people who were designed and were skilled and were specialized in thinking buildings abstractly and detached from their material representations, and people who were specialized and skilled in taking notational systems, plans, elevations, sections, etc., and enacting them and making them physical in reality. That allowed for a process where nowadays through a collection of notational systems, plans, facades, sections, whatever, we can actually envision, we can actually imagine it, we can actually elucidate, we can have a glimpse, an imaginary glimpse of what that building would look like if it was completed. And we train ourselves in doing that. It's part of what going to architectural school is. But this completely changed the way we practice architecture. And I always find extremely interesting that when it comes to architecture, we live in this world where we think architecture abstractly, we materialize it, maybe or maybe not, but we can even talk about it. We can judge if it's good or bad. We can argue about just with these notational systems. You know, and if you've ever been to an architecture, to a studio critique, all the conversations about the good and the bad and the best and the worst is happening over nothing. In which field in the world have you seen a group of people evaluating the validity of a design without actually seeing the design, only seeing the notational representations that we have all agreed to that can be used to represent architecture, right? I find it extremely interesting, the idea that we can judge something that doesn't exist. It's like, imagine music school and people judging a music piece only by reading the score, but nobody plays the actual composition. Can you think about that? That sounds extremely strange to me, right? But it's only in architecture that we can or we have to behave this way because we can't afford the actual building of these things and then judge them, right? It's an interesting process if you think about that. Representational systems evolved for many centuries. It was kind of the technological process that happened in the 15th century, 16th century, 17th century. The idea that we developed notational system, we developed perspective, we became better at representing systems, and we became more standardized and having a system that we all agreed to as a way of representing architecture. But we also, in a way, started using these notational systems as a way of thinking architecture through. So the act of drawing a building is argued by many as a process that enacts thinking that architecture, and a process that we typically refer to as design. Design is, for many of us, the iterative process of trying things out, drawing as a tool, and using that drawing process as a thinking mechanism, right? Making something a sketch is a vehicle to thinking about what that sketch represents, like in this case, a building. And it's very opposite to the concept of production. So the generation of exhaustive sets of documentation for the perfect reproduction of the building so that all the details are clear is actually two very separate processes. What you call like the initial sketching phase, the design phase, and the way we draw architecture in that sense, and the way we produce documentation for the production of architecture. It's two very separate. They also, in a way, have split parts, if you will. So there's, in a way, we have developed two different languages about how we represent architecture for design purposes and the language that we use for its representation for production. So you can see where I'm going with this, obviously. With the invention of computers, very soon followed a full set of software and particular machines, hardware like specialized printers and plotters, etc., so that the process of designing and making things was more cohesive and was more streamlined. This process started being called very early computer-aided design. And it was very heavily embraced by the aerospace industry and the car industry, the automotive industry, because in these particular cases, computers solved a very particular problem that was present very early in aerospace design, which was solving the difficult problem of representing and visualizing complex curvature in three-dimensional space. So it was back by the times when Bezier and the Casteljoux were coming up with the mathematical models to represent smooth curvatures. But in paper, we still didn't have the good techniques to do that. So computers actually came in at a very good moment to help with that particular process. But still, in computers, modeling was very abstract, was purely formal. It wasn't informed by material considerations. It wasn't informed by fabrication processes. It was a very abstract process that happened digitally. And many people argued that the detachment of the digital detachment that software has brought into the design of things has its drawbacks, because if we don't incorporate material or material considerations or behavioral considerations, then we're basically using software to design abstractly and to create form that is independent of materials. And then when we actually try to impose that form on particular materials, it becomes a huge problem. And that is relevant, for example, for anyone who has tried to do digital fabrication with wood, for example, and you realize that wood is not an obedient material like steel might be, like molten plastic might be. Wood has veneers, it has particular isotropic structure, but wood has a behavior of its own that is very difficult to tame with digital processes if you don't account for that process, for that behavior beforehand. Same with fresh clay, for example. I've done a lot of clay 3D printing in my life, and it's very hard. It's very difficult to work with fresh clay. It just doesn't want to do whatever you tell it to, you know? So there are many authors these days thinking about how fabrication processes can be changed around so that instead of imposing form on particular materials, we can use general fabrication processes to extract form from this process, something that Manuel de Landa calls the morphogenetic potential of materials. The division of labor that we've been talking about has also somehow permeated to the distribution of specialization when it comes to making physical things. So modern separations between making and doing are at every level, at the level of people who specialize in computation, people who specialize in designing with computation, people who specialize in making with computation, the control, the mechanism, the design of the machines. There is very little integration between all the roles that are present in making something physical. And there is often very little integration between all of these agents. So for example, if you think of a typical 3D printing process, 3D printing is very linear. It's a process where you start off from some kind of 3D model that you put in a software. This is where you as a designer have agency. But then after that, there is some kind of workflow of different platforms. For example, the first one taking the model and then passing it through a slicer that gives you this thing called G-code that you then plug into the machine, and then you press a button, you hope that the machine makes these things. And if something fails in this process, you have to start all over again. There's no feedback loop, there's no intervention, there's no real-time decision-making with the way we use these tools. Digital tools to make things start with some digital information that we have agency on, but they do not allow humans to be part of the making process because they come from a legacy of large industrial machines that want to make things repetitively, efficiently, but without human intervention. Humans in factories are a liability. They are a safety hazard. They're not meant to be there and making decisions. So that's why many authors already these days are also advocating for new modes of making things with digital tools, such as, for example, interactive fabrication, etc., etc. How are we doing? Oh, we're doing terrible on time. Oh my God. I'm so not going to be able to finish this. Any questions, comments, ideas? Well, let's take a closer look then at the role of computers in all this process, in the process of how do we think the things that we design. Now, the first computer that ever existed, you might be familiar with this, it was called the analytical engine or the differential engine by Charles Babbage. The first computer was theoretical. It was actually never built until very recently. I think they finished like a mock-up of from the plans and the drawings that he had, something like in the 20 years ago or so. But the first computational machine, the analytical engine, was a thought construct that would be able to compute numbers in an automated way, mechanically, with the goal of producing logarithmic tables, which I'm not going to get into why that was important in the 19th century, but it was the modern way of automating doing computation and doing like large sets of calculations by avoiding human error. Now, the design was by Charles Babbage, which was this kind of humanist in England in the late 19th century, but it was done somehow in collaboration with Ada Lovelace, who was more interested in the idea of how the machine could be controlled to exhibit different behaviors. So in a way, Ada Lovelace was the first person to consider that a machine could be programmed and that could be changed physically to perform different kinds of calculations, which was a very, very groundbreaking concept. If you think about it, computers actually first started with the telegraph and with a device that used electricity to signal to represent something that could be or not. So a 0 or a 1. And tons of aggregations of those zeros and ones became the foundation of more of the modern architecture behind computers. Today, computers, so in the 50s, first early computers were purely mechanical constructions. So they were physical machines with tons of cogs and gears and physical parts that moved all around the place. And if you have been, or if you're ever back here on campus at the GSD at Harvard, we have a copy. We actually have one of the earliest computers, the Mark I, who is on exhibit at the Science Center. And also nerdy note, this was also the first computer that had an error that started not working. And when the people who were running the machine started looking into the machine, they found out that there was an actual bug in one of the cogs, and that was preventing the machine from working. And then, so this was the first documented case of a computer bug. And then this concept was popularized by Grace Hopper, who was also one of the earliest pioneers in computer programming. And the concept of a computer bug stuck since from there on. And that came from physical computers that had physical cogs and physical moving parts. It wasn't until the contributions of John von Neumann, who was the first pioneer to conceive a computer that was made of physical parts, but that had a programmable part who could change the behavior of this computer. The idea was that before John von Neumann, computers had to be physically changed and physically rewired to perform different calculations. But John von Neumann was the first one to propose an architecture for computing machines, actually called the von Neumann architecture, so that machines became programmable. This I find really interesting because in a way, it also signals this split between machines that can only perform one action and are designed specifically for that computation, and machines that become general purpose, that become general computation artifacts, and that can be programmed using different techniques, using programmable code. This I find relevant because it's also, in a way, the earliest manifestation of splitting the functionality of a computer from its mechanical representation to another abstract thing that is code, running on the machine. And it also, in a way, is a metaphor for this separation between making things and thinking, designing how to make those things. Is the modern computational separation of how to make things and how to design software that runs on machines that make things, in this case, computation. Nowadays, of course, we all think of computers as things that can do whatever, and the software that runs on them is what defines what they do. But that is a modern concept. That is a concept that was coined like 10 or 15 years after first early computers were actually designed. If you're interested in the story of all of this evolution from the telegraph to computers, I very strongly recommend this book by Charles Petzl, The Hidden Language of Computer Hardware and Software. It's a really, really good book, very easy to read and very well written to understand the evolution of this lineage. So the von Neumann architecture gave us what we now consider the all-purpose computation machines. The idea is that the von Neumann architecture liberated machines from the slavery of doing the exact same process all the time and turned them into all-purpose computation machines, whose behavior could now be controlled by this additional layer of what we call now computer programming. What also this meant is that computer programming, in a way, liberated computational machines from the bias that they may have been designed for. Now, computers, we hear a lot about how computers bias us in particular ways, whatever, but there's actually many early authors, such as Nelson, who in the 70s, they were already saying that computers have no nature, they have no character, they have no inherent bias, and all the bias that comes with computers is the bias that us programmers embed in these machines with the software that we design, which we may or may not agree with, but I think it's a very interesting concept, and it's a very interesting one, especially in contrast with modern conversations, such as, for example, Patrick Schumacher and his idea of parametricism and how computers bias us to design buildings that have nerves, curvature, and blah, blah, blah. All of that, I don't think it's inherent in the machine. I think it's a different kind of bias, but it's something that maybe we can talk about in the conversation part of our meeting today. But the idea that these general purpose computational machines could be an integral part, they could come hand in hand with the way we evolve as humans, was already super early. It was already present in the mind of many scientists who saw computers as a liberation of the human mind. Because before computers, the humans were, if you will, scientists were burdened with the need to, for example, acknowledge or gather as much of the previous scientific knowledge as they could by means of reading articles, reading papers, reading books, etc., a process that before the computer and before the internet was very manual. I'm not sure if you remember going to a library to find a book, and then by reading this book, finding other books that you found were interesting and then studying them. This is something that we still do to a certain extent, but it's much more automated for us because we have tools that allow us to link knowledge between us. So for example, we have the internet, we can find any scientific article in the world. We have Google Scholar that links all that knowledge together. But so we can, in a way, offload a lot of our cognitive load, a lot of our memory needs to trusting that there is a system that we can use to access knowledge in a fast and reliable way. But that was not the case until like 20 years ago, even. That was not really the case. Many scientists saw that the computer could come an integral part in the way computers could partner with human minds and then offload a lot of the mundane computational tasks, but also the memory ones, and help us by indexing knowledge so that we could get to the stage of parsing that knowledge, processing that knowledge, and proposing a new one at a faster rate. And for example, in the case of Vannevar Bush, he envisioned this machine called the Memex, which had like, a touch screen and it indexed scientific articles between each other. It was like a really groundbreaking concept in 1945, something that it took 70 years to materialize in what we now know as the internet, computers, etc., etc. He was also part of a group of thinkers in the mid 20th century who thought that computers could become the new assistive, could be the new relevant tool as an assistive. They called them clerks back at the time, but to be aiding in human processes by augmenting the human intellect. This was super interesting because the idea that computers so early on, and at a time where they were still humongous machines that had to live in a room and had to be shared by scholars at a university using terminals and timeshares, etc. The fact that the people were thinking of them as hand in hand, our clerks, direct assistance, problem solving, and offloading our mental offload to them, I think that was very visionary and that was very interesting. Many of other authors were talking about computer symbiosis, man-computer symbiosis, and the idea that we could teach them by examples. And many early authors also saw how the role of computers was to amplify the human intellect. Due to this inherent non-bias present in computers, computers had the potential to reflect and to increase the user's own intelligence. And this was said by many people who in the 80s and in the 90s were now at a point where they were researching, now that computers had moved from mainframes in universities and in military installations and had moved to personal computers and were starting to become available to the masses, there was a lot of thinking back in the times about what the role of computers would be now that we could see how each person in the world eventually will end up having a computer or access to one and being able to work in partnership or in symbiosis with them. This gentleman here is Alan Kay. He was one of the pioneers on interface design. He was the one who popularized object-oriented programming as a concept, and he received the Turing Award in 2003 for his contributions. I'll get back to him later in this talk. So going back to the Neumann architecture for computers and programmable machines, the challenge now with machines that could be programmed and that didn't require mechanical engineering knowledge, that didn't require someone to know how to physically change a machine. The challenge now that we could program machines without knowing how they worked was, how do we do that? How do we create systems that allow us to change the behavior of a physical artifact without needing to teach people how the physical artifact works? This was a huge challenge. There was a huge question in the 50s about how do we provide access to computer programming for the masses now that it's not needed to learn how to physically change these machines. So this was a challenge that was akin to the one that Alberti had to face in the Renaissance, which was how to develop an abstract notational system that was detached from the materiality of the machine, but was comprehensive enough and understandable enough so that other people could use it and pick it up. And that was when the concept of computer programming and computer programming languages was born. The idea is that at the earliest stages of computer programming, this separation still hadn't really happened. At the early stages of computer programming, the way computer was programmed was using what's called machine code, which is basically a form of binary code that relies on the programmer to know how the registers and the memory addresses and the loop cycles inside of a CPU actually work. And the way computer programs were designed was very much tied to the way computers behaved in a technical digital way, if you will. Imagine the analogy here would be manual cars. So when you're driving a manual car with a stick, you have to do this process of like shifting gears. But the idea of shifting gears, it's a very low level. It's not very abstract because it's very much tied to the way a physical car works and the way that you have gears and you change those gears, whatever. It requires like some knowledge of how a machine works in order to make that process correct, right? However, obviously, very early on, computer programmers thought that this process was not very sustainable and they required a lot of training and was very prone to error because it was very abstract and it required a lot of technical expertise from the programmer. So there were many people who were thinking that there needed to be a more abstract, a more higher level way of representing how to give instructions to a machine. And that's where the idea of designing a programming language that was higher level came in. And actually, there was a huge problem. There were conferences. Even the UNESCO held conferences in the 50s and the 60s where computer programmers gathered and they highlighted the necessity to create computer programming languages that were standard, that were popular, that compile, etc., but that provide higher level structures that didn't require the mechanical or the technical expertise of knowing the computer. So in this sense, three main figures from back in the times, from the 60s and then 70s, could be highlighted as early pioneers of computer language design. And the first one of them was C.A.R. Hoare, who's is, for example, regarded as the inventor of the quicksort algorithm. He invented the switch case. If you've ever done switch case as a conditional statement, he was the one who invented that. And he received the Turing Award in 1980. And he referred to himself very often as a feature designer. He is also he also invented null objects and null references, what he calls his $1 billion mistake. And if you're nerdy enough, Google him because he has a lecture where we talk about the invention of null pointers and how that basically messed up the whole world of computer programming and how he regrets that. It's super, super interesting. But what I like about Sir Charles Anthony Richard Hoare is that in his writings, he is very, very verbose and very eloquent about describing computer programming as akin to craftsmanship. And how in all spheres of human and intellectual activity, from carpentry to golf, from sculpture to space travel, the true craftsman is the one who thoroughly understands their tools. And that to him also extends to computer programming and computers. Computer programs should be about understanding the problem and the programs rather than focusing on the tool itself, which I think was a very interesting approach to designing computer programs. Also, Edgar Dijkstra was one of the earliest pioneers in computer programming design. He is very well known for the Dijkstra search algorithm, and he received the Turing Award even earlier. He had tons of writings and tons of paper where he describes programming as an activity that is elegant, that is worthy of our love, and that should be no different from any other craftsmanship. And that it shouldn't be considered, computer programming should not be considered as a science, but it should be considered as art. And very interestingly, a lot of his papers were actually not scientific publications, but they were handwritten papers that he wrote to his colleagues, his peers, his friends, and that are now at an archive in the University of Texas at Austin, I believe they are. Very, very recommendable reading, very humanistic, surprisingly. And last but not least, Nicholas Wirth, who is the only one who's still around. And he was also one of the earliest pioneers in computer programming design. He developed Algol, he developed Pascal, he developed Modula, Oberon, all of them programming languages that are not that popular or in that much used these days still, but with many feature designs that made it to other modern languages, such as, for example, Python, and such, for example, JavaScript. We can talk about that later. He received the Turing Award in 1984. He coined Wirth's law. So are you familiar with Moore's law? The idea that computers become doubly powerful every 18 months, and how that law is kind of not working anymore because we can't make chips smaller enough anymore. Well, he coined Wirth's law that says that software gets slower as hardware gets faster. The idea is that he was very cranky, he is very cranky about how with the advent of computers that are way more powerful and that are more capable, we kind of indulge in code that is sloppier and less efficient just because we can run it on computers and we don't have to care about performance anymore. So he is also very eloquent, and he has talked a lot about the idea of, for example, the levels of abstraction in computer language design and the art of designing computer programs to solve intricate problems. He is, and he was, and he still is very, very critical of some modern programming languages, such as, for example, C. He's one of the biggest enemies of C as a programming language because back in the 60s, there was this huge current of trying to make computer programming languages higher level, and he saw C as a language as many, many steps backwards towards this idea of an intellectual, high-level, abstract language, for the reasons for how C brought back memory pointers, addresses, etc., etc. All right, but now we have programming languages. We can program machines. How do we actually feed those computer programs to computers, right? The first interface to make that happen were punch cards. And if you are not familiar with them, they're basically sets of physical cards that had 10 registries. And by punching them and running them through a machine, you could, with a code, like for example, ASCII, you could create literal text. So for example, this punch card that we have here is representing a function of C equal to I to Y plus function W of 1, whatever that means in Fortran. And this was inspired, as you may already know, by the Jacquard loom, which was arguably the first programmable machine, the first CNC machine, if you will. And but what was interesting is that in order to program machines, we actually needed other machines to create those cards. And what we can see here is a Jacquard loom card puncher, where by passing, for example, a design through a grid of set numbers, and by punching those numbers manually in the card, we could create the cards that create this design in a Jacquard loom. This process, the process of punching cards, was extremely tedious, extremely time-consuming, very prone to error, very difficult to double check, very difficult to debug, and it needed tremendous specialists in order to make it happen successfully. And guess what? Very early in the age of computer programming, the people who actually specialized in punching these cards and transcribing computer programs and designing them were actually women. And this is something that is very often not acknowledged in the history of computation, which is kind of sad, but because it was a task that superficially looked similar to that of a clerk or that of a secretary, that's why armies of women started being the ones who created punch card programs and who transcribed those and who generated, for example, like a 4.5 megabyte program that looked something like this in punch card terms. Obviously, you can imagine how storing these things, keeping them in order, not messing them up, not trimming, it was a huge deal. They were easy to lose, they were easy to misplace, etc. It was a disaster. So mainframes became very soon the way to interact with, so terminals became very soon the way to interact with mainframes, so that you could queue and those punch cards, but then you could start accessing them in a way that was more human friendly. So punch cards led to teleprinters, they led to tape, they led to computer terminals, and screens and keyboards, also inventions that happened during the course of the 50s and the 60s, provided more fluid interfaces to the design of computer programs that led to higher levels of interaction. All of this crystallizing and all of this popularizing with the advent of, with the move from mainframe computers to personal computers. All of a sudden, in the 80s, when computers were accessible to everyone, then we didn't need specialized scientists or business people who needed to be highly trained in order to use a machine. Machines, computers, all of a sudden were part of the popular culture, were accessible to anyone. And therefore, further work needed to be done to abstract even more all the tools that we use to control computers and to make this accessible to everyone. At this point, with personal computers, we could not afford to use highly sophisticated computer programs such as Fortran, whatever, or to demand that anybody knew how to program a computer for the same matter. So that's where the development, for example, on graphical user interfaces, the idea of the desktop as a metaphor, the idea of like the relations, that the graphical relations that we provide for users, all of this, the idea of human-computer interaction as a field was born in the 80s, because since it was not a domain of highly trained specialists and scientists anymore, but it was something that had to be done for the masses, it became a field on its own. It was very interesting because, for example, in the early 90s, the main tool that we used for design tools was the metaphor. And there was so many conversations at the Apple labs, at the Xerox labs and all that about how the metaphor that we provide, so for example, the desktop, the window, the trash can, all of those were the main tool for design of computer interfaces. But also many people were arguing how it was, how it had difficulties and had a lot of drawbacks. It could become a dead weight, it could become a false metaphor, it could become a confusing part, and the magical aspects, the ones that are not part of the original metaphor, could lead to confusion or to the affordances. Furthermore, computers were at this point machines that we used for functional purposes, not for creative purposes yet. So for example, the development of computer screens was fundamental. And
in this research activity, the designer and computer are conversing in a graphical language, as two designers might discuss and adjust a drawing.
And there was a promise of human-computer interaction.
He tells the computer that he wishes to modify the design. So the computer responds by giving him the requested statement from his program.
Could you hear the sound? So in the 60s, when all this was happening, there was the promise of the computer will respond to you. The computer will give you what you ask for. The computer will be your partner, your subservient, there will be a certain degree of intelligence in the computer. However, we all know that that was not really the case. And that when it comes to design, earliest and perhaps still the best example of computer-aided design was Sketchpad from 1962, just because it was one of the earliest and one of the strongest examples where the computer did have some agency in proposing, in responding, in modifying, in correcting designs that were generated by a human. Also, quick note, Ivan Sutherland received his Turing Award in 1988, also for his contributions to computer graphics and to human-computer interaction. However, many authors from that age were also rethinking how computers could be active partners in design processes. And for example, the work of like a lot of work was a lot of work came unnoticed from back in the times. Like, for example, there was this thesis called Pygmalion, a creative programming environment by Smith from the Xerox labs in 1975, which was considered by many the first creative programming environment. It was the programming environment that, for example, coined the idea of icons. It was out of this thesis that the idea of an image representing a concept that could be draggable and it could be actionable, that was invented with Pygmalion, and the idea also of drag and drop as an interaction was also generated by Pygmalion. It's a beautiful dissertation if you ever want to read that. But it was supported by the idea that images are representations that aid cognitive processes. It was very important when computer screens were popularized to capitalize on the idea that images were a much richer way of conveying meaning than 1,000 words, basically. And that's what computer-aided design tried to be. That's what the ideas where CAD was trying to capitalize on. But unfortunately, I don't think these ideas picked up that much because at the end of the day, digital design back in the times was purely a translation of what was happening in drafting tables, but in a digital way in a screen. The example was early versions of AutoCAD, where all the parametric relationships, all the smartness that was designed by Ivan Sutherland in his Sketchpad, none of that actually made it to commercial products out there in the world. And it's kind of unfortunate. And many authors have argued that bad software has led to bad tools, and that that has led to the de-skilling of designers due to the fact that we're using tools that are not giving us expressive potential, that are not giving us freedom to express ourselves. I think Bill Mitchell's work is extremely relevant in this case, how he advocates for software as a means of accumulated knowledge, as a legacy, that is transmitted generation to generation, almost as guilds used to do, and how today we stand on the shoulders of giants and of tons and tons of people who have created lots of technological environments, digital, software, computers, physical, that have led us to more empowered ways of designing. And this is very relevant, for example, today in workshops like the one you are attending, where we are using a lot of tools that other people have provided for us. And the question here is how those tools act as an agent for the de-skilling of our agency, or how we can capitalize on these tools to enhance, to augment our creative capabilities. And I think that's where I would like to stop, because I actually have to go very soon. So I'm sorry this took a little longer than I expected, but thank you for sitting through all this brick of of ideas. And I think at this point, we could probably open it up to questions, comments, ideas. I have 8 minutes.
Yeah, thank you so much, Jose, for your wonderful lecture. Yeah, I think we'll like to open the stage for the audience. So is there any questions, comments, ideas? Alrighty, even now I actually have like a question about like the idea of like machine intelligence in architecture, because you're actually the like the first like the founder for this like workshop name, and it's like I have to credit you for last year's successful workshop Indeed the Future. It's under the machine intelligence in architecture. Yeah, and so I think my question would be like, what do you think like would be the difference between the concept of machine intelligence and the artificial intelligence, like which a lot of people or architects use today in the in the similar context? Yeah.
Sorry, I couldn't hear that well. Can you repeat the
sorry.
question?
Yes, I think I would like to maybe propose like just the first question is like, what do you think like would be like the difference between the concept of machine intelligence where you use it for the workshop and the artificial intelligence where which is used a lot in other workshop titles and in the same context? Yeah.
Yeah. So when I also want to make credit Nono Martinez Alonso for the coining of the term machine intelligence. That was something that we've been discussing for a long time, back and forth. You had him here give a lecture a couple of days ago, right? So I think for us, machine intelligence is a way of breaking away from this kind of strong separation that I perceive out there in the field between people who talk about artificial intelligence and people who talk about machine learning. And the idea being that the later people who talk about machine learning are typically data scientists and people who are obsessed with linear regression and like convolutional networks and all the statistical averaging and weighing techniques that we use to predict things, right? And then the idea that machine learning can lead to something that can be perceived as very narrow intelligence, so an intelligence that is really good at performing one particular task, a very narrow one, like for example, discriminating between cats and dogs, or like identifying objects in an image, right? But it's very far away from that holy grail of an all-purpose intelligence that is okay or decent or good at performing many different tasks that require creative thinking. Like, for example, the one we attribute to humans. We think of ourselves as good at overall intelligence because we're flexible, we're adaptable, and we can solve problems that we have never seen before. Whereas we have not created machines that can mimic that all-terrain expertise, if you will. Contemporary machine learning, contemporary neural networks are exceeding our skills in very, very narrow focused tasks, like for example, detecting tumors or like predicting when weather patterns are going to, something is going to, those kind of things. However, and doing computation, computers are really much better at us at crunching numbers, but they haven't really reached that state. So that's why machine learning is kind of a field that sets itself as a problem-solving kind of technique, whereas artificial intelligence, I often see conversations around artificial intelligence more in that other vein, the track of discussing how computers can mimic the versatility, the adaptability of solving general problems. And even sometimes it gets mixed with the whole ordeal of sentience and self-awareness and terminators coming over and killing all of us and becoming machine civilizations and all that kind of stuff, right? Which is a whole different topic. I think when it comes to using machine learning for creative purposes, there's a gray area because when it comes to defining what is the problem that we want to train a neural network for, if it is a very quantifiable problem, like predicting when an electric central station is going to blow up, we have gotten really good at very concrete, very tangible problems. But those are not the problems that we typically face when we are doing design, when we are thinking architecture, or when we're trying to come up with creative applications of machine learning. Therefore, defining loose problems, defining open-ended goals, and using machine learning to inquire these problems is very difficult these days. And you're probably facing this in your own work in this workshop, where design is a very open-ended task. It's a very iterative, the goals change, etc. And therefore, machine learning is still not a great tool, or it's one that it's difficult to tame for these purposes. But it's a task that is closer to this overall all-purpose intelligence. And that's why Nono and I, when we thought about the term, we thought that it could be interesting to talk about machine intelligence as using machine learning techniques to try to solve creative problems that were a bit more open-ended and where the goals were not so clear. And because it's a term that kind of sets you somewhere in the middle between the idea of artificial intelligence and machine learning, and as these two extreme poles of specificity and generality. Does that answer your question?
Yeah, that's really perfect. Yeah. Any other question from the audience?
Yes. Hi, Jose Luis. I just wanted
Hi, Carlos.
I just wanted to at some point you mentioned some sort of bias that, for example, what Patrick Schumacher had mentioned in the 90s, and I don't know.
Careful, if you say his name 3 times, he will show up.
Right. Yeah, that's true. That's true. I mean, I'm just saying that because I think it's interesting the way you spoke about the different type of eras and that are related to the way that to the tools that we use to produce things, and you know how people started using the spine lines in the 90s, and now we're doing discrete things. And I don't know what the bias will be now that we're using AI or machine intelligence. What do you think things are going to start to look now that we have the ability to control these tools in AI?
So things that are going to happen is, first, they're going to be hopefully very soon sometime, there's going to be an increased awareness about reflecting on the biases that we bring to the neural networks that we train. So typically, we think of bias in machine learning as something that is bad, because we typically want machines to be as unbiased as possible. And this is very relevant for applications of machine learning out there in the wild that are affecting human lives. So obviously, I don't agree with using neural networks to screen people or to pre-screen CVs for a company, or to assess the risk of someone for insurance purposes. I think it's a terrible thing to do. That's my opinion. That's my ethics, right? And that's why biases are typically a thing that we want to avoid by balancing data sets and by trying to, all the techniques that we do. So there has to be a lot of criticality and ethics when it comes to that. Now, the opportunity here is that it turns out that for creative purposes, biases are not a terrible thing. Actually, biases are things that we sometimes look forward to, because if you think about it, the architecture that a particular well-known studio, like I'm going to say, I don't know, Frank Gehry, Zaha Hadid, all of those studios produce architectural objects that have a very strong bias, and such a strong bias that you can tell them apart, that you can see images of a building and you can tell if it was designed by Stephen Hall or Daniel Libeskind, or, you know, and that is because having a language, having a set of properties, having features that define you as a style are kind of features that are sought upon as a form of signature, as a form of trademark, as a form of authorship in today's times. That is the origin, a little bit of Patrick Schumacher's conversation about parametricism, and how, for example, the idea that Rhino is now so popular among people who design architecture, and therefore nerves are extensively used for design architecture. That's what has led to this new style, parametricism, that is not, that he talks about as a style, not as a personal style, but as a global style, because it's used by many people, like Gothic, like neoclassic, like etc. etc. It's not, it doesn't belong to a person, it belongs to an era, if you will. So the idea of bias is interesting. It gives us authorship, it gives us a style, it gives us a name, it gives us a property as authors. And it's interesting that machine learning frameworks have all these biases because we can train them on those biases. Now, my only concern is that we can borderline ethical problems by doing so, but at the same time, just as it happened with Voronoi in 2009, it was a tool that was all of a sudden available in Grasshopper, and everybody started doing Voronoi, and we all got sick of Voronoi so fast, you know. Latent walk navigations and like spiny, blobby architecture images and blah, 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 they're going to get old very soon, just because it is the default style, and that comes from all the convolutional and all the layers that happen when you downsample images and the architecture behind neural networks, etc. We're seeing a lot of that, and we're going to get very tired of that very soon. It's a matter of all of us now technically and conceptually trying to figure out what can we do and how we can take these neural networks to find our own personal language within them. And that is what I hope to see very soon. So at a point where we all have enough technical expertise to really fine-tune these neural networks to create results that we can own as our own, and that are different from the standard that can be produced with these tools these days, out of the box. Those are my 2 cents, you know. And I need to apologize, but I have to go. I have a commitment at 10:30, so I need to move on. It was a huge pleasure to be here. I'm very happy to see a lot of familiar faces, actually. And thank you very much to everyone. And I hope you have a blast. And maybe I get to see you tomorrow. But otherwise, you know where I am. You know how to reach out to me. Happy to follow up. Okay.
I postponed my question till tomorrow, but I just wanted to say hi because it's been a long time that I haven't seen you, and it's a pleasure always to see you. So thanks,
Likewise.
Jose.
Likewise.
Thanks, Jose.
Thanks a lot. Bye bye.
Thanks, Jose.
Thank you.
Yeah, thanks so much.
Bye.
Thank you.
All right, everyone. Yeah, I think we're gonna stop the live stream